This is lecture number 14 of electronic devices. Here the subject is electronic devices and the subject code is KEC 301. Today's topic is diffusion current. So, before starting today's lecture, let me introduce myself. I am Dr. Sapna Katiyar, Professor in Electronics and Communication Engineering Department at ABES Institute of Technology, Ghaziabad. After the completion of today's lecture, you will be able to understand what is diffusion current, what is this diffusion process, how to write down the diffusion like terms, how to derive the equations mathematically. At the same time, we will discuss about the Einstein relation also. Let us begin. To start with this diffusion, first you have to understand, if you are able to understand the diffusion, the topic will be very much clear to you. What is diffusion current? See, diffusion can be understood as the random thermal motion of a particle from a region of higher concentration to a region of lower concentration. This is the statement, you can write it. So, what is diffusion in general? Let me give you a very practical example. See, if you have two bottles which are filled with the water and those two water bottles you are not keeping at the same level. One bottle you have kept like this, the second is like this. If you have connected both the bottles, so what will happen over there? So, water from this particular bottle will be passed on to the bottle which have been kept at the lower level. After a certain time interval, you can observe that the level of water in both the bottles will be same. So, this is what the diffusion process is. As I have told you, it can be understood as a random thermal motion of particles because we are dealing with the semiconductors, that is why we are talking about the particles random motion from a region of higher concentration to the region of lower concentration. Means wherever there is a concentration difference, their diffusion process will takes place. You can see in this particular diagram, here in this first case, if we talk about the semiconductor and let us say there are the electrons which have been shown over here. These are the electrons. So, in this diagram you can see non-uniform distribution. Here non-uniform distribution. What will happen? After certain time, these electrons on the left hand side you can see the concentration is very high, on the right hand side the concentration is low. Electron concentration is high on the left hand side, electron concentration is low on the right hand side. So, what will happen? These electrons tends to move from a region of higher concentration to the region of lower concentration, means from left to right, and after certain time you will find a uniform distribution. You can observe in this particular pattern the concentration of electrons in this entire piece is uniform. So, this is how you can understand the diffusion process. And current conduction in semiconductor, it may occur because of the diffusion of carriers, as I have discussed. This means the carriers are moving from a region of higher concentration to the region of lower concentration. And second factor is the drift of charged particles under the applied electric field. In the previous lecture, I have discussed about the drift current. Drifting is what? If there is a presence of applied electric field, if there is a presence of electric field, then the charge carriers, if we talk about the semiconductors, means there must be some electrons, there must be some holes. So, then because of this applied electric field, electrons will move, electrons will tend to move, holes will also move. So, you are going to say that there will be a drift in velocity for the electrons and drift velocity for the holes. And drift is what? To be carried out, means electron will be carried out in one direction, holes in that other direction, and accordingly you can understand that. So, it means the current conduction, for current conduction these two things are important. First is diffusion and the second is drift. So, I hope these 2 points are clear to you. Now, let me give you some more examples via which you will be able to understand more clearly what is diffusion actually. See the first example, putting a drop of dye in water. If you put a drop of dye in a water, what will happen over there? You are just putting a drop So initially you are going to observe that there is a drop, but after certain time what you are going to observe, that drop is spread out in the water. It means what? Drop is spreading out means there is a diffusion from the higher concentration from that particular point where the drop was actually available. That was the reason of the higher concentration. It is diffused means now after certain time it has been diffused equally into the entire one. It means now there is a uniform distribution. Second example is opening a bottle of perfume in a closed room. If you open, you used to see this particular example in your daily life as well. If you open a bottle of perfume in one corner of the room, what will happen? Initially you will find the fragrance at that particular corner, but after a certain time interval, if you move to the other corners of the room, you can also observe the same intensity of the fragrance you will find everywhere in that particular room. Means now initially the intensity of the fragrance was very high at one point, but after a certain time interval, the overall room, the entire room is being like fragranted. You can find the same intensity, same smell of the perfume. So this is because of what? This is because of the diffusion process. So I hope now this particular diffusion process must be very much clear to you how to explain it, right? You can take many more examples. Let us discuss some more basic terms. Diffusion current occurs without an external voltage or applied electric field. As I have discussed many examples, you cannot find in each and in any of the example that there is a application of the applied electric field. Diffusion, if you are putting a drop of dye in a water, there is no applied electric field. If you are opening a bottle of the perfume, there is no applied electric field. It means diffusion current occurs without an external voltage or applied electric field. Diffusion current does not occur in a conductor. Conductivity is also high, means diffusion current will not occur over there. Now let us discuss how this diffusion process can be explained and how to represent it mathematically. Here you can see a diagram. A curve is being plotted actually. On the x-axis distance is being taken, on the y-axis we have taken the electron concentration. You can see at these 2 points, let us take a point number A and point number B. Electron concentration, you can find the concentration at point number A is high in comparison to the concentration at point number B. Distance is less at this point if the distance is x1, at this point if the distance is x2, x1 is less than x2, and the concentration of like electrons is high at point A. So after a certain time interval, as the distance is being increased, what happens? There will be a change in the concentration of these electrons and it will decrease from a point A to the B. So this is how this particular curve is being explained. Means there is a change, there is a variation in the concentration of electron with respect to the distance. Distance is being taken as x. So you can say concentration gradient. Concentration gradient, this is very important and you must be able to write it down mathematically, then only you are going to derive the other equations. See, concentration gradient for n-type semiconductor. If we are talking about n-type semiconductor, means definitely what are in the majority? In n-type semiconductor, majority charge carriers are electrons. That is why we have plotted this particular curve. If you had to deal with the concentration gradient for the holes, you have to take the holes concentration variation because the holes are in the majority in case of p-type semiconductor. So here concentration gradient can be written as what? Jn is directly proportional to dn upon dx. Variation of distance, variation of electron concentration with respect to the distance. And see, there is a decrease. It means wherever required, you have to consider this minus sign as well. Since there is a decrease, so you have to apply this minus sign, and in some of the cases, you have to take it into the consideration. So this is how you can write down the concentration gradient. Now, concentration gradient for p-type semiconductor, Jp is directly proportional to dp upon dx. dp upon dx is change in the concentration of holes with respect to the distance. So, this is how you can written over here. I have told you about this as well. Now, let us discuss in detail about the diffusion current density. Diffusion current density, because of the electrons, you know that Jn is directly proportional to dn upon dx. As I have told you also that there is a decrease in the concentration of electrons with respect to the distance, means there will be a minus sign, and when you have to exclude this particular proportionality term, you have to include a proportionality constant. So, from here you can write down Jn is equal to what? Q is the charge on the electron. Charge on the electron is minus Q, it is negative. Let us put minus Q. dn upon dx, there is a decrease. So, we have to put a minus sign as well. Into, to remove this, we have to introduce a proportionality constant. So, we have included a proportionality constant which is dn. dn is the diffusion coefficient for the electrons. See, minus minus sign will cancel out, this will be plus, that is why you have written what is Jn. This is Q into dn upon dx. Similarly, diffusion current density due to holes. See, you know that Jp is directly proportional to dp upon dx. There is a decrease in this, so you have included minus sign. dp is the proportionality constant which you have included over here, and q is the charge on the hole. Charge on the hole is positive plus q, that is why there is a minus sign over here. So, the equation is Jp is what? Minus q into dp upon dx. Here you are finding two terms, one is dn. dn is the diffusion coefficient for the electrons and dp is the diffusion coefficient for the holes. Now, the total current density to the electrons. See, we have discussed about the current density. Current density because of the electrons, current density because of the holes. But when you are we have discussed about the drift and diffusion, both the phenomena. So, in general, the total current density, it will be the sum of what? If you are calculating the total current density because of the electrons. So, for electrons there is a drift current, for electrons there is a diffusion. So, we have to consider both the terms, drift current plus diffusion. So, what is this Jn? The term for the drift current is Q into N into mu N into E. Q is the charge, N is the concentration of the electrons, mu N is the mobility of electrons, E is the applied electric field, Q is again the charge on the electron, Dn is the diffusion coefficient, and this is the concentration gradient. Accordingly, the total current density due to the holes, which is the sum of drift and diffusion, this can be written as what? You can see over here there is a minus sign is why? Because we have written the diffusion coefficient for diffusion current, which is Q, which is the charge on the hole, into diffusion coefficient, which is dP, into the concentration gradient, and since there is a decrease in the concentration gradient, so that includes minus sign. So, that is why here the sign is negative. So, you must note down both of these equations. These equations are very important. You may get a number of questions. Calculate the total current density because of electrons, total current density because of the holes. If you have to calculate the total current density due to the electrons and holes both, means in the previous equations we have discussed about the current density because of electrons, current density because of the holes, but now in general the total one, that will include the current density because of electrons and holes. So, what you are going to write over here? J is what? First, Jn is Qn, mu n is the mobility of electrons, into E plus Q, charge on the electron, Dn, diffusion coefficient, into Dn upon dx, which is the diffusion coefficient, plus Jp, the first term is Q into P into mu P into E. P is the concentration of holes, mu P is the mobility of holes, E is the applied electric field, plus Q, charge on the hole, dP is the diffusion coefficient of the holes, into dP upon dx, which is the concentration gradient for the holes. So, this is how you can calculate the total current density. So, now you have written 3 equations: current density because of electrons, total current density because of holes, and total current density because of both the electrons and holes. Now, here a very important point, you must note it down. What is the difference between drift current and the diffusion? This is a very important point. You may get a number of questions based on this. Basic difference between the drift and diffusion. See, drift current depends on the electric field. If there is no electric field, there is no drift. Means drift of charge carriers, drift of electrons, drift of holes will be there if there is only presence of the applied electric field. In case there is no electric field, means there is no drift in the charge carriers. Diffusion current occurs even though there is no applied electric field across the semiconductors. I have given you various examples also to explain you, just like you are opening a bottle of the perfume. If you are opening a bottle of the perfume, there is no applied electric field, there is no applied potential, even then the diffusion process takes place. It means in the presence of electric field, drift will take place, while in the absence of electric field, diffusion will take place. So, this is a very important point, you must write it down. Now, let us discuss about the Einstein relation. Einstein relation, this topic is also very important. So, you may get a number of times the derivation based on this. So, and the basics for this is the diffusion, the equations which you are getting from the drift and diffusion. See, the equation which relates the mobility, mu, mobility is denoted by mu, and mobility means by which the charge carriers are moving. Charge carriers are electrons, charge carriers are holes, means how the charge carriers are mobile. So, the equation which relates the mobility mu of electrons or holes and the diffusion coefficient of electrons and holes is known as the Einstein relation. Means there are 2 parameters, there are 2 coefficients, one is the mobility, other is the diffusion coefficient, and the equation which derives, which gives the relationship between these two, that is the actually Einstein relation. Now, some of the basic points let us discuss. First, mobility characterizes what? Mobility characterizes, see, you are saying that person is very mobile. It means how quickly that person is moving, how quickly the assessment is being done. It means mobility in terms of when we are talking about the devices, when we are talking about the semiconductors, mobility characterizes how quickly an electron or hole can move through a semiconductor when there is a applied electric field. See, whenever there is a applied electric field, there will be some drift, some movements among those particular charge carriers. It means mobility characterizes that particular movement, and the process of electrons or holes moving from the region of higher concentration to the region of lower concentration is known as the diffusion. So, I am just going to tell you all the pointers via which we are going to derive that particular Einstein equation. So, I hope now this diffusion process is also clear. Diffusion is a process of moving from a higher concentration region to the lower concentration, and mobility, how quickly charge carriers are moving. Then, drift current density of electrons or holes is directly proportional to the mobility of electrons or holes. We have discussed that the drift velocity Vd is proportional to the mu n or mu p. So, drift current density of electrons and holes is directly proportional to the mobility. From here you have derived the equation, you have written the equation Vd is what? Mu n into E, which is the drift velocity because of the electrons. If you are calculating the drift velocity because of the holes, that will gives you what? You have to consider the mobility of the holes, which is mu p into applied electric field. Next is the diffusion current density of the electrons and holes is directly proportional to the diffusion coefficient. Diffusion coefficients are denoted as Dn, means the diffusion coefficients of holes, dp is the diffusion coefficient of the dn is the diffusion coefficient of the electrons, dp is the diffusion coefficient of the holes. So, diffusion current density is of electrons and holes is directly proportional to the diffusion coefficients, right. Remember all of these points, these are going to helpful in future. Now, let us assume an electric field is in x direction. You can see in this particular diagram, see, this is the valence band is being shown, this is the conduction band is being shown. In between the valence and conduction band, this intrinsic level have been drawn over here. If the applied electric field is in the x direction, plus x direction, now electrons drift opposite to the Ex. If electric field is in the x direction, electrons will move towards the opposite direction, minus x direction. Therefore, potential energy for electrons to increase in the direction of the field, this electrostatic potential which is written by Vx, it varies in opposite direction, and this electrostatic potential can be written as what? Vx is what? E upon q, charge on the electron is minus q, that is why we have taken minus q. So, Ex upon minus q, from this particular equation number 1, you can explain, you can calculate the electrostatic potential which is because of this particular applied electric field, right. What this particular electrostatic potential is being influenced, being observed by the electrons. Now, from the definition of electric field, you know what is electric field? Change in Vx with respect to the x. X we have taken along this x axis. See, on the horizontal plane we have taken the x parameter. So, what is Ex? Ex is nothing but, since there is a change, minus d upon dx of Vx. Let us say this is the equation number 2. Now, from equation number 1 and 2, just you substitute the value of Vx from equation 1 to equation 2 and write down the term for the Ex. Ex is what? Minus d upon dx. Substitute this Vx term over here, which is Ex upon minus q. Now, because you have to choose some particular value of in between energy, particular value of the energy level in between the valence band and the conduction band. So, besides choosing any random value, let us take a intermediate value, and this intermediate value is represented by Ei. It means now Ex will be what? This is nothing but, see, d by dx of this particular term, q is a constant, minus minus plus 1 upon q d upon dx of Ex. But on that particular large scale, whatever the value you are going to calculate, you are going to evaluate, you have to generalize it, so that whatever the equation we are getting, that must be practically applicable for all the things. So, that is why we have taken the simplest case, the intermediate value, and this Ei level we have taken over here. This is the equation number 3, which you have written for the Ex, for the electric field. Remember this. Now, we will derive one more equation for the Ex, and then we will equate both of these equations and we will further simplify it. It will be helpful for us to derive the relationship between the mobility and diffusion coefficient. So, I hope now it is clear to this particular point how you have written this equation and why we have taken our intermediate value, which is Ei. Now, you know that the total current density is what? Total current density, you can take any of the terms. You can take the equation for the current density because of the electrons, you can take because of the holes, any equation you can take, and from that we can generalize it. So, here we have taken the current density because of the holes. This is what? Drift current plus diffusion, means for holes, this total current density, this will be because of the drift process, because of the diffusion process. You are aware with this particular equation. So, what is Jp? Drift is q into mu p into p into E. Why we have taken x? Because there is a variation with respect to the x. Q is the charge, mu p is the mobility for holes, p is the concentration, and since concentration is varying with respect to the x along the x axis, Ex minus q charge, dp is the diffusion coefficient of the holes, and d of dx of px is what? The concentration gradient. So just we have utilized the equation which we have derived earlier, and we have written the term for the total current density over here. At equilibrium, you must remember that no net current flows in the semiconductor. At the equilibrium condition, no current flows. It means Jp will be 0. So let us assume this particular case, the case of the equilibrium, if this is the current scenario, if this is the situation, and if Jp is equal to 0, then let us substitute in this equation number 4. So this particular term will be 0. What you are getting over here? This term is equal to this term. Q mu p px ex, this is equal to this term, and from here you have simplified it and written the equation for Ex. Ex is what? See, this is dp upon mu p into 1 upon px into d of dx of px. Just you have rearranged the term, and now you are getting the equation of Ex, which we have mentioned as equation number 5. Here we have to take one more assumption and we have to analyze it, because you have to derive it finally. So whole concentration varies from intrinsic concentration when Fermi level moves from EI towards valence band. See, if you observe the energy band diagram, there is a valence band, there is a conduction band. In the case of the like p-type semiconductors, since the concentration of holes is very high in comparison to the electrons, means the concentration of electrons is less, it means Fermi level lies closer to the valence band. So when whole concentration varies from intrinsic, means EI level, EI is the intrinsic carrier concentration, and Fermi level moves from that particular EI to valence band, means it is moving towards the valence band, and when it is moving towards the valence band, means there will be an increase in the whole concentration. So Px can be written as what? Ni, which is the intrinsic carrier concentration, exponential EI minus EF upon Kt. K is the Boltzmann constant and T is the temperature over here. This is the equation number 6. Now what you have to do? In equation number 5, you have to substitute this value of Px, because dp you know, mu p you know, the only thing is Px, which is in general. So now we have to simplify it. So let us substitute the value of Px from equation number 6 to equation number 5, Px over here and dy dx of Px over here, and you have to simplify it. You can check it out. Ex, which you are getting, this is what? dp upon mu p into 1 upon kt, and this term you are getting as d upon dx of EI minus d upon dx of EF. EI is the intrinsic concentration level, EF is the Fermi level over here. So in this particular manner, you can now simplify this particular equation, and you must remember that at equilibrium, Fermi level do not vary with x. Since we are talking about the equilibrium, there will be no change in the Fermi level, and when there is no change in the Fermi level with respect to the x, then what will happen? This particular term will be 0. D of EF upon dx, this term will be 0. Now you can substitute this term is equal to 0 in the equation number 7. So you are getting Ex is what? dp upon mu p into 1 upon kt dEI upon dx, because we have substituted d of dx upon EF as a 0. From here, just you are rearranging the term, you will be getting, see, 1 upon q. Now we are equating the equation number 3 and 8, both of these equation. We have derived the value of Ex in this from this particular equation, and earlier we have also discussed. So when you have equated the equation number 3 and 8, you are getting dp upon mu p is equal to kt upon q. This is what we have derived for the holes. Similarly, you can derive the equation for the electrons, which will be dn upon mu n, which is equal to kt upon q. You can generalize it as well. In general, you can write down d upon mu, which is equal to kT upon q. This will be the general equation. It can be modified for the electrons, for the holes, as I have written for holes for electrons. So, what are these coefficients? dP is the diffusion coefficient of the holes, dN is the diffusion coefficient of electrons, mu p is the mobility of holes, mu n is the mobility of electrons, Vt is the volt equivalent of temperature, which is equal to K into T upon Q. K Boltzmann constant, T temperature, and Q is the charge. If you substitute the value of K and Q, you will be getting Vt is equal to T upon 11600. So, this is how you can derive the Einstein equation. You must remember, this is very important equation. So, I hope now the diffusion process, diffusion current and Einstein relation both are very much clear to you. Thank you so much.